Section 2.1 covers the molecular model of an ideal gas. Here we are approximating a real gas using a very simple model where essentially the molecules are assumed to have no volume and not interact with one another. So this is an approximation. It tends to work well when the density of the gas is very, very small. And therefore, the volume of the molecules is insignificant, and the interaction between the molecules is also not all that great. So an ideal gas, again, is an approximation. Now, if we place a gas in a container, we know that a gas basically takes the shape of the container. Therefore, the container's volume becomes the gas's volume. We look at the relationship between pressure, volume, temperature, and the number of molecules, the number of moles, and relate them to one another using an equation of state. And that's exactly what the ideal gas law is. Now, you're not used to seeing this version of the ideal gas law if you've used it in chemistry class or you've used it in other classes. Normally, we see it as PV equals nRT. Okay, we'll get to that version a little bit later, but we're looking at the ideal gas law in terms of pressure in pascals, volume in cubic meters, sticking to the SI system, number of molecules. So that's going to be a really, really large number. If we have 1 mole of gas, we have 6.022 times 10 to the 23 for the number of molecules. We have Kb, which is the Boltzmann constant. This is a very, very small number. And then finally, we have the temperature. And this is very important to remember that this temperature is in Kelvin. There's no degree sign there. So we assume that it's absolute temperature. It is the Kelvin scale. Now, again, an ideal gas. We think of an ideal gas as a collection of atoms or molecules that are moving randomly. They exert no long-range force on one another. So that is one of the approximations that we use, that there's no intermolecular forces between the molecules, that they basically collide with the walls of the container. Each particle is also assumed to be point-like. So any volume that the molecules have will have no impact on the state equation. If we do those two approximations, we can come up with our familiar ideal gas law. Now, oftentimes, because that n that we showed you before, the big N, the number of molecules can be a very, very large number. We replace n, or large N, with a small n, which is the number of moles. The number of moles is equal to the total mass of the gas divided by the molar mass. That's the number of kilograms or grams per mole of a particular gas. So for instance, if we have carbon-12, okay, and that's not normally a gas, but we'll use that as an example, 1 mole of carbon-12 will be 12 grams. In fact, Avogadro's number is related to the mole carbon-12 and the fact that 1 mole of carbon-12 weighs 12 grams and has Avogadro's number of molecules. All right, again, Avogadro's number, this is a very, very large number, just as the Boltzmann constant is a very, very small number. Avogadro's number is 6.022 times 10 to the 23 molecules per mole. So if we rewrite our ideal gas law in molar form, we replace N, capital N, and Kb. We replace those instead with small n and the universal gas constant, R, which is 8.31 joules per mole Kelvin. Again, it's just another convenient way of writing this if we want to avoid using this absurdly large number for number of molecules and this very small constant right here. Sort of brings things a little bit more more realistic, or at least the numbers closer together to one another. So again, ideal gas law, we can write it either way. PV equals capital N kBT using the Boltzmann constant, or PV equals nRT using moles. Now we are going to come up with this equation of state. Can be demonstrated experimentally, but we can actually derive this basically using mechanics. We can use kinematics, describing how the molecules move, and look and see how collisions with the walls of a container will lead to the generation of a pressure. Okay, so kinetic theory of gases. Again, the assumptions are the following. The properties of gases are important in a number of thermodynamic processes that depend on the behavior of the gases. Many of these properties can be calculated to a good approximation using the kinetic theory of gas. Here, the number of molecules in the gas is large, and the average separation between them is large compared to their dimensions. This is the requirement for the ideal gas law to be valid, and this is what we're going to use to derive the ideal gas law. Large number of molecules, but they're separated by enormous spaces compared to their own volumes, and they don't really interact very much. The molecules obey Newton's laws of motion, okay, kinetic theory, but as a whole, they move randomly. All right. The molecules interact only by short-range forces, essentially allowing them to elastically collide with different bodies such as walls or other molecules. Okay, let's see where these equations come from. Again, air can be pretty much assumed to be pretty close to an ideal gas. It's one of the most important gases to living things on Earth. We know that our atmosphere is mostly nitrogen, about 3/4 nitrogen, about 1/5 oxygen. And this is something that varies a tremendous amount. Water vapor. Water vapor can be very, very low, as the case in extremely dry areas such as the desert or Arctic regions, or it can make up a much larger percentage of the atmosphere as it does in tropical regions. Other trace gases include argon, neon, trying to think of some of the other gases that are present there. But again, they really don't make up a very significant fraction of the atmosphere. It's mostly nitrogen and oxygen with quite a bit of variability of water vapor. Now, for a gas, we have a number of different laws that allow us to relate the different variables in the equation of state. And all of these can be put together to create the ideal gas law. The first thing that we can demonstrate that for most gases, again, we're assuming a fairly low density, is Boyle's law. It essentially says that if you hold the number of molecules constant and the temperature constant, that the product of the pressure and volume will also be constant, okay? Basically, if you think about it, PV equals nRT, if N and T are constant on the right-hand side of the equation, P and V have to be constant on the left-hand side. So we can imagine two different gases. Let's take a look at the gas in this container right here. We see that the volume is large, so that for a given temperature, we would expect the pressure to be lower. If I cut the volume in half, then I would assume that I have to double the pressure. Again, if V2 were 1/2 of V1, P2 would have to be twice the amount of P1. And this makes sense. As you try to compress a gas, you make the volume smaller and smaller. Its pressure gets larger and larger as more molecules attempt to, or as more molecules collide with the sides of the wall more frequently. Again, this is Boyle's law. Another important law, besides Boyle's law, is the Gay Lusek Law. Basically, this relates pressure and temperature. Now, again, all other properties have to be constant. The number of molecules is held constant. If we hold the volume to be constant in a closed container, as we raise the temperature, we know the pressure of the vessel is going to increase. Okay, so let's say we look at a container of gas, it's at one temperature, and then we double that temperature. Again, when we're talking about doubling temperature, we're doubling the absolute temperature. So let's say we start at a low temperature of 200 degrees Kelvin, and we raise the new temperature to 400 degrees Kelvin. Okay, now look at this. If I take T1 and I double the temperature, T2, and make it twice as large, for a given pressure, the pressure is going to also double. Again, this is known as Gay Lusek's law. So the ideal gas, again, law combines all of these pressure, volume, temperature relationships into one law. And again, understanding what pressure is proportional to the number of molecules per unit volume, but also the average translational kinetic energy of the molecules. Essentially, if we had one single molecule bouncing around in a container, we would only experience a force when a collision took place. But again, if you have 1 mole of gas, you have 6.022 times 10 to the 23 molecules colliding with the wall. So instead of the pressure varying or only taking place when a collision takes place, there's so many molecules colliding at any one time that all of this pressure evens out and the pressure is pretty much constant. So again, think about it. How do we increase the pressure if the pressure is related to the molecules colliding with the sides of the wall? One, you can increase the number of molecules, okay? More molecules mean more collisions more often, more force. Pressure is force divided by area. That's going to raise the pressure by introducing more molecules. But I can also increase the pressure by increasing the temperature, because the temperature is the average kinetic energy of all the molecules. So if I'm speeding them up, think about what happens. Not only are they going faster, so they're going to hit the wall more often, but when they hit the wall, they're going to hit with a greater force. And again, pressure is force divided by area. So we can increase the pressure by increasing the number of moles or molecules. We can increase the pressure by increasing the temperature. We saw that really happen in both of the former laws that we went over. Now, look at this right here. This is rewriting the ideal gas law, PV equals capital N KBT, okay? And putting KB off to the right-hand side, okay? So look and see what we have here. First of all, we have Boyle's law. PV is going to be constant, all right? If temperature and the number of molecules are constant, and the Boltzmann constant, of course, is a constant, PV will be constant, and that will be Boyle's law. Boyle's law works for constant temperature, constant number of molecules, okay? The Gay Lusek law, pressure divided by temperature is a constant, again, if the volume is held constant, if the number of molecules is held constant. In fact, there are other laws too. The Charles's law, volume divided by temperature or temperature divided by volume is constant if the number of molecules and pressure are held constant. We have Avogadro's law, which states that the volume divided by the number of molecules is constant. okay? And of course, we have the combined law, PV over T is equal to a constant, is also there. So all of these laws, which were demonstrated long before the kinetic theory of gases, all of these laws are consistent with the ideal gas law. So here are all the summary of the gas laws. Boyle's law, which we talked about, the Gay Lusek law, which we talked about, Charles's law, Avogadro's law. And again, each of these laws basically says that, some combination, pressure times volume, volume divided by temperature, pressure divided by temperature, volume divided by the number of moles. All these are constant if the other physical parameters are held constant. We put them all together, they result in the ideal gas law, okay? And again, these all work usually as long as the density of the gas is not too high, or we're not near a phase transition where the gas is beginning to approach a temperature and pressure where it's going to liquefy or turn into a solid. Now, again, ideal gas law. It's good, but again, it's only an approximation. It assumes that the molecules collide elastically, which to the most part they do. At higher temperatures, they might begin to ionize atoms, break off electrons, but for the most part, these collisions in normal circumstances are going to be elastic. There's no intermolecular forces, except for when they get very, very close to one another, as long as the molecules have a good separation between them. And the molecules occupy no volume, or the volume is so small compared to the empty space the molecules don't occupy, that the volume of the molecules is insignificant. Now, a better approximation happens if we include intermolecular forces and molecules are given a finite volume. The biggest problem with the ideal gas law is this. The ideal gas law does not allow for phase transition. There's no phase transition. So according to the ideal gas law, a substance can never become a liquid or a solid. If we use the van der Waals approximation, where we allow for intermolecular forces, we will see that phase transitions, especially phase transitions to liquids, are possible. In addition, we also, by giving the molecules a finite volume, allow the pressure to change non-linearly with increased density as the molecules begin to get very, very close to one another. Now, like any model, as the model becomes more sophisticated, the equations become harder. The ideal gas law is easy. PV equals NKBT, or PV equals nRT. With a van der Waals approximation, we add other things going on here. Now, again, here's our ideal gas law up here. That's nice and compact, simple, allows us to relate the state variables, pressure, volume, number of molecules, and temperature. And now here is the van der Waals equation of state. And notice I've got some additional terms here. Now, in the ideal gas law, we just had the number of moles appear on the right-hand side of the equation. Now with this approximation, we're going to have number of moles appear in what's called a volume term, and the number of moles appear in what we call an intermolecular attraction term. Okay, let's see what's really going on here. Now, normally, if there are no intermolecular forces, the P would just be by itself, okay, as it is in the ideal gas law. Now, if we include intermolecular forces, what these intermolecular forces are going to do is create an attraction which pulls the molecules together and is going to cause the pressure to drop. So the stronger the intermolecular forces, the greater the decrease in pressure. The volume term takes into account that if the molecules occupy a particular volume, that is going to reduce this volume term, which is going to cause the pressure to go up. Okay? As the molecules get closer and closer to one another, they're going to basically crowd each other out and raise the pressure. So it gives us a much more complicated equation. In fact, when we graph the equation, we can see that it produces some interesting results. Now, the van der Waals equation, basically, when we graph pressure as a function of volume, and really we should go back and talk about the ideal gas law. The ideal gas law, if I graph, let me get a graph up here. If I graph, let me do pressure on one axis. Let me do volume on another axis. If I graph pressure as a function of volume, our expectation is P equals N KB T for a given temperature, number of molecules, divided both sides by V. I'm going to get a relationship that looks like this. Let's see if I can draw this. Okay, that's what it's going to look like. All right. For a higher temperature, it might look like this. For a lower temperature, it might look like this. It's going to give me this inverse relationship. All right. Maybe this is at a temperature of 500 degrees Kelvin. Maybe this is at 400 degrees Kelvin. We call these isotherms, by the way. Maybe this is 300 degrees Kelvin and so on. All right. Nice inverse relationship between pressure and volume for a given temperature. Nothing too complicated there. Now, if I graph pressure versus volume for the van der Waals equation, we get these weird dips, okay? Instead of having a nice 1 over V relationship for the pressure, we get these little dips here, which are due to the attractive forces of the molecules, and then we get this sudden increase here due to the volume effect. Okay. Now, this is not a physically possible solution. What happens here is instead of getting these dips and then these rises right here, as we see right here, a dip and then a rise like this, we actually flatten these out, call these tie lines, and it basically says that you can't really have two pressures and two the same pressures for different volumes, is what it's really saying. That's not physically possible. Otherwise, we could have pressure here, pressure here, pressure here. So we sort of flatten this out. I misspoke there. You can't have a lower pressure for a smaller volume, is what I meant to say. And if we graph with this alteration right here, what we get is a much more complicated phase diagram. Okay. Now let me just show you what's going on here. All right. Up in this upper right-hand corner, we basically have a gas. It follows pretty closely to the ideal gas law. Okay. But as we approach these lines right here, the intermolecular forces and the volume effect become greater and greater and greater, until finally what happens is once I cross this line right here, over here, I get a liquid. Okay. So you've got your vapor over here, you've got your liquid over here, and in between the two, okay, it's about 50% liquid, 50% vapor. Then finally it becomes 100% liquid or 100% vapor over here. Okay. So the ideal gas law is really powerful for low density gases. However, when we start getting into phase transitions, it breaks down. Like many simple approximations, it breaks down, and we have to use a more complicated law. And again, here's just another phase diagram with the different isotherms. Again, at high temperature, the relationship between pressure, volume, temperature, and the number of molecules, well, temperature is held constant here, is basically an inverse relationship, okay? PV equals nRT describes this pretty well. But again, as we start getting to lower and lower temperatures, where we have the possibility of it liquefying, we start seeing these little hitches here due to those special terms, and finally it liquefies. So ideal gases, again, can't liquefy. There's no attractive forces that would allow them to liquefy. But of course, taking into these van der Waals forces, these intermolecular forces, we can form liquids. And again, this is just another graph showing the same thing. By the way, TC on this phase diagram represents something called the critical temperature. Basically, any temperature higher than the critical temperature, you can't have a liquid, okay? In this particular case, this cannot be liquid above 647 degrees Kelvin, because essentially, the molecules are going to have too much energy in order for the van der Waals forces to hold them together into a liquid, okay? Below the critical temperature, we can have a vapor, we can have both phases existing at the same time, or we can completely have a liquid. There's also critical pressure, okay? And again, the critical pressure represents the pressure the gas would have at this critical temperature for a given volume. So let's look at some different substances and their critical temperatures. So we see that ammonia will not be a liquid above 132 degrees Celsius. And ammonia was actually used as a refrigerant originally. So it was a very, very important material. And one of the reasons why it was such an effective refrigerant is because of its ability to change phase at a fairly low pressure. The only problem is it had a tendency to blow up. So it was replaced with fluorocarbons later on, which were less reactive than ammonia. Ethanol cannot be a liquid below 241 degrees Celsius. And of course, water is no longer a liquid at any pressure above 374 degrees Celsius. And here's helium. Helium is normally a liquid at 4 degrees Kelvin. And methane also can be liquefied. It's liquid natural gas in any case. But again, those are some critical temperatures and some critical pressures.